I am Lennart. Hi, my name card says Lennart. So I'm a PhD student at the Paderborn Center for Parallel Computing in, well, Paderborn. There I've been doing my PhD now for a little over 1.5 years, and my topic is the design of a new hardware design language named SUS. But first, I'll do a bit of an introduction with some lighter slides, just an emotional catch to get your attention. I like hardware design. I've been doing it for many, many years, actually all the way since I was a child. I have hardware designs in many, many other little games. So for instance, here, I think all of you will recognize this one. I have a few more obscure games after this as well. Where I had built like a CPU, 6-bit analog CPU in Minecraft using like the signal strengths of redstone. And so you had like your little ALU built-in register into that, and then 3 registers down there that have like increment and decrement functionality. It was like a whole fancy thing, and I had like ROM and everything. Kind of the idea was to make a computer as small as possible in Minecraft, so you could actually build it in survival. But yeah, I mean, I never put all of the parts together, so it never became a real computer because I kept optimizing this damn thing too much. But in my spare time, or usually during work hours, if I'm procrastinating on building my hardware design language, I'm doing hardware design in Constructor. It's like, I don't know, does anyone recognize this game? No, wow, no takers. Okay, it's a Zachtronics game where you basically get p-doped and n-doped silicon, and you get to like place it on the map, and then you get to build little transistors that are either like PMOS or NMOS transistors, and you're asked to build various hardware designs. So in this case, this I can proudly present is a 8-bit addressable read-write memory. So you got your address decoder and your memory there. Real fun stuff. Also, wow, it's difficult to think about if you're putting this down. But where my hardware design experience or path really started is in another game. Any takers for this one? I mean, this was a... Yeah, that's cheating. So it's actually not my screenshot, because from when I was 7, I don't tend to have any screenshots from my PlayStation 3 remaining. This game is Little Big Planet. It's a game about building 2D levels where you can have switches and lights and doors, and so you have little logic gates that you can use with that as well. And of course, people go bonkers with them and build whole CPUs with them. Now, my hardware design path became a little more serious once I was actually in university. And so a project I did there was the following. These are some screenshots of the die of the FPGA for the accelerator for the 9th Dedekind number. So long story short, it's basically the project that brought me to PC Squared. Because at PC Squared they have some really unique hardware in their cluster. The only cluster that really could take advantage of the hardware designs that I was building for accelerating this computation of the 9th Dedekind number. After about 3 years and a humongous hardware design later, we actually managed to find the number. And so you can now look it up on Wikipedia. We've been credited with the discovery of this behemoth of a number. And actually, I have pencils of it if you want one after this talk. It fits real neatly, actually. And so, yeah, this was basically my biggest hardware adventure thus far. But during my work, I felt very dissatisfied with the existing tooling, and thus, when I had the opportunity to do a PhD, I chose the topic to improve the hardware design tooling that we have. A little more word about PC Squared. So this is my home turf. Up there is our beautiful Noctua 2. She has, yes, it's like a ship, you know. She has 1,100 servers with 128 cores each, 128 GPUs, and then critically, because barely any other compute centers in Europe have this, Noctua 2 has 80 state-of-the-art acceleration FPGA cards. So these are a far more niche high-performance computing platform. They are mostly used, at least as far as I know, either in data center networking or high-frequency trading. These are like the two main use cases. And so these cards, they're not cheap. They're like, actually, I'm not supposed to say any numbers. They're also very, very difficult to develop for. And so, yeah. What really attracts me to hardware design is low-level optimization. It's the process of tinkering, measuring how your edits made it better or worse, forming hypotheses, how could I adapt my hardware to be better, and seeing if your hypotheses actually work. And this really is the feedback loop that really drives me to do hardware design. Within hardware design, very often you get this give and take between your algorithm and your implementation. Like you have some algorithm, you go and implement it, and you see, what I have available on this FPGA is actually not that well suited, and maybe I need memories of 4096 or 92 bits deep, but I actually only have at most memories of 2000 deep. Maybe I can alter the algorithm a bit such that I can more effectively make use of my memory blocks. And so you have this give and take between the algorithm and the implementation. Sadly, doing this kind of tweaking with current state-of-the-art tools still is a pain. Some people just forgo it altogether. They reach for HLS, and then they get a design that technically works, but they would not be able to say, is it optimal? Am I using my hardware well? And why does it only go up to 220 megahertz? So SUS is all about the process of hardware design. It is to make it possible to do little tweaks, to improve your code, to move things around without much mental overhead. Of course, being a proper hardware design language, we need to have full control. So this will highly limit what kind of abstractions we can create. And we can only, the philosophy in SUS is if you can draw it, you can write it in SUS. So that means we can only provide tools to deal with the complexity, to kind of have the compiler think with you, but we can never have the compiler think for you. Another point in this regard, the netlist is the main focus. So really with SUS, you're designing the netlist, how your gates and registers are connected to each other. And of course, you want to actually synthesize your designs. You want to see what do Vivado, what do Quartus say about the timing of this design, where are the bottlenecks, what is my slowest path, etc. I say Vivado and Quartus because on these high-end FPGAs, there are no open source tools available because, well, Intel and AMD, they very tightly keep the gates locked. And, oh. Fair. So we need to use Vivado and Quartus, and we need to work with them. Finally, something I've noticed about many of the competing languages is they don't tend to have all that great developer experiences. Like with Chisel or with Spinal, you're writing Scala, and I mean the IDE, it can give you great Scala-related information, but it can't really give you information related to your hardware. And so with SUS, a large part of the design is designing the language to be able to utilize modern IDEs well. And there's like little hints in which you can see that happening in SUS. So the minimum of IDE performance of IDE support, of course, is your syntax highlighting and error reports, where, for instance, here we've created a feedback loop of hardware. Where should I stand? The beamer is a bit low. Where we've created like a feedback loop that has a net positive delta latency. You'll learn a bit more about latency counting in some later slides. But first, I will get you a bit accustomed to the SUS language by example. So here is how you would design an XOR gate. And in the spirit of sus, like you can write it. That is exactly the case. And this is how you could naively write an XOR gate. And we have defined the module here. It's called XOR. We have our two inputs, we have our output, and then a bunch of intermediate wires. And so these directly synthesize to logic. It's not that you go through this statement by statement and like execute it. No, it directly describes the structure, like the data dependencies between your wires. And this is a critical thing that sets it apart from like software languages, of course. To instantiate it, we have here named our interface XOR. It's a special case which allows us to instantiate our module inline such that you can get function-like module instantiations. And in this case, it's just a simple true-false. Of course, hardware by its nature often contains very repetitive structures. Some languages, like indeed the Scala or Python embedded ones, they go full in, they give you a full Turing complete language, but they sacrifice a lot of the IDE feedback for that. And so you can, with these languages, generate any hardware you want, but it's less easy to interact with your hardware. Sus also has compile time code. It is in the form of generative code. You can see here these two nested for loops. And if you were an HLS programmer, you would expect these to get synthesized to like a state machine that would then, through one multiplier, send the data one cycle after another. But in Sus, we do no such thing. So in Sus, we these two for loops, they synthesize 600 separate multipliers. Because the important part of Sus is that you're describing your hardware directly. And if you want to have cycle-to-cycle behavior, you need to actually create cycle-to-cycle behavior. This is such that we have a close connection to the hardware that we actually generate, such that we can take this feedback from our synthesis tool and apply it onto our hardware that we're writing. So just another little example to get more accustomed to the language is FizzBuzz. Who here does not know what FizzBuzz is? One hand, three hands, three hands, okay. So FizzBuzz, it's a common interview question, basically to test the reasoning of their interviewee. The question is, you get a value, you check, is it divisible by 3? Then you should output fizz. If it's divisible by 5, you should output buzz. Both, you should output fizzbuzz, and otherwise you output the value itself. And so, in this case, I've implemented it in Sus. So we create two intermediate wires that basically check if they're divisible by 3 and 5. And then we have a bunch of if statements that synthesize to a multiplexer over here to pick which case. Of course, I'm outputting an integer. I don't get to print line in Sus, so I had to make do. But many synthesis tools, they don't support synthesizing modulo and divide operations. And so what if instead we would want to implement this module as a lookup table? Well, with Sus, with the generative code system, we can actually generate this lookup table when we synthesize the module. So here, you can notice the small difference. We've created this generative variable LUT, and then we've added gen to our fizz and buzz computation, and pretty much all of the others are the same. And so instead of doing it at runtime, we compute for the entire table all of the values that we should output. And then the only statement that actually turns into real hardware is the one all the way at the bottom. This FB is our LUT of V. And the fun thing is, because I've invested quite a bit in the editor tools, on hover, the compiler can tell you what is in this lookup table. And actually, this was a complete surprise to myself when I first bumped into it, because I had just included it because, well, if I hover over a generative variable, what should I print? I guess we have the last value of it somewhere, so I'll just print that. And it turns out to be useful because you can see the last state of all of your variables when, say, execution of a module has crashed. And so you basically have debugging right in your editor, which is really quite useful. So any competent hardware design language needs to have parameterizable modules. Verilog has a Chisel and Spade and Scala, and Spinal have it. We need to have it because, well, it's just a fact of hardware design that you want to have it. So I've declared a little module here called split@. We take in a list, we cut it in half somewhere, and then we return you the two lists that you've split. So we define a type parameter for the content of the list, size of the list, and then the split point as value parameters. And then we've implemented the module to make use of these parameters. How we can use it? We can either directly specify all of our generative parameters for this module. So we explicitly specify the type, the size, split point, or we can have the compiler infer it. Yes, or we can infer it. And so this is actually really quite new, this inference, because it is part of the latency inference that I've been doing in the last couple of weeks. Once we have parameterizable modules, we can also, of course, do recursive modules. Actually, a lot of hardware structures are these recursive tree structures. And so, now that we have them, we can implement it. Say here we have a tree adder. So let's say we get a list of 1,000 numbers. Well, we don't want to just add up 1,000 numbers in like in a linear fashion. We want to subdivide the problem. So we add up half, and then we add up these two results. And so we implement that with this. We have the base cases. What if the list is empty? What if the list is one element? If it's not, then we split the list and we instantiate two tree adder modules of smaller size. As you can see here, the arguments or the parameters for these modules have been inferred based on the types it finds around the modules. To make this possible, to kind of walk this very fine line between being able to generate any hardware and being still able to give good programmer feedback, SUS has two levels of typing. Because, maybe I'll just show you this. Because let's say we're trying to assign one array to another array, and their sizes are determined at compile time by some function. Well, if we want to type check this for all possible parameters, then it becomes a problem called dependent typing. And dependent typing is, I mean, it's great for writing hundreds and hundreds of papers about. It is less great to actually have in your compiler. And so with the abstract and concrete typing system SUS has here, what we do, we get the non-monomorphized code, I guess is what LLVM calls it, where we have not yet instantiated any of our template arguments. And we can do abstract typing on that. So we know, okay, this A is an int array. We just don't really care about what size it is. B is an int array, or out is an int array. And so we can already eliminate a whole swath of bugs or of incorrect hardware before we actually have to instantiate the module. That helps the programmer to immediately catch errors before they even have instantiated the module. And it also gives more information to the IDE, where you can already hover and see, okay, a certain value is a certain type. It can help for, say, code completions. Like if I say my type dot, and then what are the contents? It needs to know that this was a struct of a certain type. Now, once we have actually executed the code, and I mean that literally, when we actually instantiate this pairwise multiply, we will execute the for loop, and whatever runtime hardware it like passed over, that gets generated. So equivalently to the top hardware, when we instantiate this module with size 3, we get these two lines here that are the equivalent for this specific parameter set. And now that we have concrete values and concrete integers for our array sizes, we can do concrete type checking. And we can see, okay, are all of our array indices in bounds? If I'm assigning arrays to arrays, are these sizes the same, etc. And so by having separate abstract and concrete typing, we can kind of get the benefits of both worlds. Of course, it's twice as much typing implementation work, but I'll take that on. So then we've come to the latency counting part of the SAS compiler. Because in my experience, when people build hardware designs, they generally tend to use registers in two distinct ways. Either the registers are part of the core functioning of the design, like the cycle-wise behavior of the design would not work without these registers. But on the other hand, like when Vivado tells you, oh, your negative slack is like negative 12 nanoseconds, or is it positive 12? It's been a while. If it tells you have bad timing for your clock, then you want to add pipelining registers to improve the longest path of your design. And SAS covers these with so-called latency registers. So, an example for state registers, let's say we have a little module to generate Fibonacci numbers. We declare 2 state registers there, and the core functioning of this design says, okay, we want to generate the next Fibonacci number every cycle. And so we have our current number stored in here. We add that to the previous number, we output that, and we store this again. Our design would not work without these registers. Now, on the other hand, let's say we have a multiply or a take some value to the 17th power module. Well, this module has a lot of multipliers built in, like 5 separate multipliers here. And maybe Vivado told you, well, you want to run your thing at 500 megahertz, but the signal takes, say, I don't know, 4 nanoseconds to get from I to O. So your max clock is going to be 250 megahertz, and you want to improve that. What you would do is you would add latency registers in between here, such that now the signal doesn't have to travel all the way. It can just get stored in here and then move on to the next one. This is a very common operation that we do in hardware design. And in many languages, it's surprisingly painful. So in SAS, what we do is we compute a value for every single wire in the design that I call the absolute latency of this wire. And then with the explicit latency count register annotations there, you tell the compiler, okay, between these 2 points, there has to be at least a difference in absolute latency of 1. And so if we follow this along, that will mean the compiler figures out that O should have an absolute latency of 2 here. And from these absolute latencies, the compiler then inserts the necessary pipelining registers to balance out these latencies. So here, because of the gap, it will find, okay, I need to put a register here, I will put one here. And also because this has created a gap between these 2 wires, the compiler has to insert 2 latency registers there to keep everything in sync. There's quite a few languages that do pipelining as like a language feature. I mean, Spade and TL Verilog, and quite a few more I can imagine. And something I see many of these languages do is they'll have like a insert pipeline stage here annotation, where it's like an @ symbol or something. And the issue that these languages run into is that they implicitly assume that your inputs will be coming in at the same time, and your outputs will be going out at the same time. And this I find too restricting of a restriction. So with the latency counting system, you don't actually need to have that. Here, the compiler can see, okay, we have a bunch of latency steps in here, but add2 is only required 2 cycles after factors. So it will assign absolute latencies 0, 2, 2, and 3 to the ports. It will do this in a way such that the inputs are always as late as possible and the outputs are produced as early as possible. And actually, it is always possible to either find the one and only optimal solution to this, or to prove that there is a conflict, that there is no optimal solution. And actually, there being no optimal solution is a real edge case. It requires you to write some really nefarious hardware. So in practice, it does not tend to happen, but the compiler, of course, still has to catch it. Because this is a critical thing. In SUS, every module that you write has some specific canonical hardware representation. Like, this is really something you need to have full control over the hardware you're writing. It needs to be well defined. Right. Now, you can always override the latency values that the compiler finds or infers for your hardware. So in this case, I've told the compiler, nope, I comes in at cycle 0, O is produced in cycle 5, and I'm just connecting them. And so this forces the compiler to insert 5 latency registers here to compensate for the latency that we have annotated. Now, where might this be useful? Let's say we want to make a shift register that takes some number of cycles. And instead of using a whole bunch of registers in a row, what we want to use a block RAM, store the values in the block RAM, and then read them out n cycles later, such that in effect we have created a shift register without actually using many of our fabric registers. The implementation of it is pretty simple. We've actually annotated the latencies on the ports manually. We declare our memory, we store our data in the memory, but then of course, to act as if this took some time, we have to give it an explicit latency offset. And this latency offset is a compiler built in that basically says, okay, without putting registers along this path, our input is at cycle 0, our output is at cycle 7, just act as if that's the case. We wouldn't actually need to specify these latencies here, but that we do specify them is something that will come up later. Right. But first, I will kind of talk about how latency information moves around in your design. So let's say we have just executed the code to generate this outer module, and then this submodule, it has not yet been instantiated. And so what we do, or what the compiler does, is it will first start by instantiating the submodule, and that gives the latency counts on the ports of the submodule. And just to remind you, this says there's a latency of 6 cycles between the 0 and the 6 port. And from the information of the latency counts of all of its submodules, it can then compute the latency count for the outer modules. In effect, latency information is traveling up the hierarchy from submodules to higher modules. But in some cases, we may want to actually have the implementation of a submodule be dependent on the environment it is situated in. So this is an example from the Dedekind kernel. It's a very simplified example. Here, the main compute pipeline is happening in these mono up and mono down stages. And to really get that clock speed in there, I had to add a lot of pipeline stages along the way. But of course, what that will do in effect is it will require pipeline stages on all of the other wires. And you can see these wires, they're quite wide. So just with these registers, we're already using I think 1024. No, it's only 600 registers with the ones we have listed here. But that's still, actually no. No, it is about 1,000 registers. So this is a lot of registers. And maybe we want to replace these with our block RAMs. Yeah, maybe we want to say, okay, replace these big blocks of registers with a block RAM. But of course, if we have to specify the size of this block RAM, then every time I add or remove a pipeline stage in these mono up and mono down blocks, our block RAM, we also have to edit that. And that is a source of bugs, of course. So with our type inference system, what we could do is we could see, okay, this block RAM module, it has on its ports a latency of 0 and a latency of latency. And if we know what kind of latency we would want to have on this line, and we could kind of, the assumption is we want to grow the submodule as big as possible without affecting the latency counts of the supermodule, then we can infer that this submodule should have, in this case, a latency of 8. And so we don't actually need to update the parameters of this module. We can just have it be inferred from the context. So that is why we would want to mark a module explicitly with the latency counts that it has. Right. So a major goal along the path of the SUS compiler project was to actually get some non-trivial project working in SUS. And so that non-trivial project ended up being the bit serial matrix multiply. So the algorithm basically works as follows. This is what you should expect to build with the bit serial matrix multiply. We need to have a preferably sparse matrix that is known at compile time. And what we'll do is, for our runtime multiplication values, we'll feed them through 1 bit at a time. Now, why would we do that? Within these rows, in a normal matrix multiply, we would have to have n by m bit multipliers. Now, DSP slices, they tend to get pretty expensive. But what if instead we were not multiplying n with m, but n with 1 bit? Then, in effect, and certainly if this n is like a constant, then the implementation for this is in effect just wires. Either, like, if your constant is, say, 25, then you would just, and like you're multiplying it by 1 or 0, then in effect you would just be building the wires that say, okay, the bit is just wired to the 1 bits of this 25 constant. Am I making sense? Okay, good. Maybe I was making too much of a point of it, but and so what you do is you take in your 32-bit values, you store them in these bit shifters, you shift them through 1 bit at a time, and then you can implement your multiplications really, really cheaply. And then, because they're just literally just adders at that point. And then you have to gather up the results again in accumulator registers, where every time we shift by 1 and add the new value, yeah, to undo the bit shifting that we've done before. So just to zoom in on one of these bit serial rows, if our matrix is sparse, then we actually have some zeros that we don't even need to care about. And then we can just take our values, convert them to the bits of each of the constants, gather up a list of all of the values for this row, and then have an adder to add them all together. So no real multipliers are in this design. So let's get implementing. We'll start from the bottom with the bit serial row. At the top, we get our size, we get our weights. We get in our bits, and we want to output the total of the row. What we first do is we count all of the non-zero values. And if it's all 0, then, well, we can just return 0, because this row did not sum to anything. And otherwise, we create a list that we gather up all of the constants that we need for this row, such that we can add them together. And so we gather up all of the non-zeros, and indeed, we check the accompanying bit. If it is 1, then we add the weight of that value into the list of that we need to add up. Otherwise, it is 0. This is just equivalent to having wires. And then at the end, yeah, only add if a bit is 1. And in the end, we add this list together with this tree add module we defined earlier. Then we have the state. We have 2 interfaces in this case. So we have an interface to start the bit serial matrix multiply. It's basically the reset signal. And then we have an interface to feed it a new bit. Yeah, so the state it gets a set of input bits. We have a state for all of our working results for the matrix multiplication sum. And we instantiate all of our multiplication rows. These are the bit serial row modules. If we're initializing, we initialize our result vector with 0. Else, when we feed, we just add, we shift what we have by 1, and then we add the result of this row to that. That was equivalent to the picture we saw at the front. Finally, we have the bit shifter. So the bit shifter, it again has two interfaces, a start interface to basically reset it, and then a shift interface to shift in, or that. Right, so the shift interface, you can see it has an input that says it should shift, and it produces the list of bits that is then fed into our bit serial state. So on start, we initialize our state block here. We initialize our state block with the bit equivalent of all of our integers. And then every shift, we just shift this whole shift register left by 1. We feed in all of the most significant bits of this. And so we do that 32 times until we get there. And so this module is not responsible for doing the 32 times, right? So putting it all together, we have the bit serial matrix multiply top module, and we get a width, a height, and our weights matrix, all generative values. We instantiate all of our submodules, so we have our bit shifter, we have a iterator that can count up to 32 values, or 32. We have our state to gather up all of our results. We plumb the start signals, we plumb the shift signals. And then at the end, this is again something curious. So we are compensating for 33 cycles of processing by shifting the latency again, such that when I call this bit serial matrix multiply module and I give it some input parameters, its output at the same time shifted in latency by, I'm guessing in this case about 36, they will match, such that in like later hardware you can use it transparently, this module, without having to think about, okay, this module takes 33 cycles. This might be the least intuitive part of the latency counting system, I give you that. So we'll use it, and we just have, we'll just set up some arbitrary sparse matrix. We pass it into the bit serial matrix multiply module, and then we plumb it through. So I just defined an extra finish signal, just such that when I was looking at the waveform, I could see where the valid values were together with the finish signal. But in effect, it just generates like 32 or 36 registers between start and finish there. And here, this is what I meant. So our result then comes out at the same time as our finish with the latency count that we give it. And so this makes it easier to see on the waveform viewer when our valid data is actually there. I'm actually hoping that at some point we can integrate with some waveform viewer to maybe compensate for the latency count that it knows from a program, such that you can kind of look at the way the hardware is behaving, completely disregarding any pipelining that is within it. So any related signals are nicely stacked on top of each other. Right, so I simply wrote a little test bench in System Verilog because, well, System Verilog, it's a language that was originally designed for simulating hardware. So let's simulate some hardware with it. And so simulate we do. Here is the Vivado simulation plot for the bit serial matrix multiply. I won't ask you to verify this. It is indeed quite difficult to look at the signals and suss out exactly what if it is behaving correctly. But trust me, it does do the job correctly. And so then I could actually synthesize it. And the fun thing is, because we are designing hardware at this very low level, we can again see from the hardware we've generated, and we can loop it back to our code that we have written. So you can just, through the module hierarchy, mark, say, the state module, the row adders, the bit shifter, and the iterator, and these all pop up as specific regions in our hardware design. And so, of course, also your timing reports, from these names, you can also go back to your hardware design as well. I will close with the architecture and future plans of the compiler. So this is what the architecture of the SUS compiler looks like right now. On the left, our SUS files come in. They are first parsed with treesitter to create an untyped syntax tree. This syntax tree is then flattened into a representation I would assume LLVM people would call your MIR or HIR. This representation, it has all of your wire assignments. It has still all of the unexecuted generative code. And this is the one that your LSP is going to be looking at the most. So this is what is used for syntax highlighting. Also, we try and do as much as possible at the flattening stage. So we'll do name resolution. We'll also do the abstract type checking. Now, once we actually instantiate some top module, we give it some default parameters, or I mean any module that doesn't have any parameters, we can instantiate immediately. And so this top module, along with all of its dependencies, then get instantiated. And in that case, or with that, all of their code gets executed and we get proper wires, multiplexers, registers, etc. On this instantiated representation, we also do our latency counting, we do concrete type checking, and maybe we can do later on hardware verification and other post-processing steps. From this representation, we can then output, so we can either generate Verilog, we could generate VHDL, which one of my students is working on right now, but there's also possibilities to generate KLX or circuit MLIR. Going up the arrows, so all of these processes can produce errors and can produce annotations. The LSP server can visualize these. Right now we just have an LSP for VS Code, but we're using the LSP protocol, so it can be applied to any other editor that supports it. Or if you're using it from the command line, it can give you command line diagnostics as well. The roadmap for SUS, so the very first release is 0.0.1 and then quickly followed by 0.0.2 release. It was waiting until we could actually implement this bit serial matrix multiply in SUS. And so the vast majority of the features you saw in the presentation were already in the language in this 0.0.2 version. 0.0.1 just did minor technical changes, so we now bundle the standard library with the compiler, such that you didn't need to actually have separate files for it. Most of the code changes, though, were internal technical work, such as switching to Hindley-Miller, which helped us a lot in the later stage for type inference. Right now, I'm working on version 0.2.0. In this version, we will add type inference, so we already have it for generative values and type parameters. What we're still looking for is this latency count inference, and cross-parameter inference is kind of a minor type of inference, but it's still useful. So the bit I showed you where the latency count information could travel downwards as well. I was really hoping to get it finished by this talk, but life happens, and so, yeah. Anyhow, we'll also add compile time functions. So a lot of the technical work was in regards to being able to do this. So we'll add clog to, size of, and assert. These are like typical functions that you would want to have at compile time. Finally, also, since the language is still in pretty early stages, we have all of our integers just at 32 bits, but a very important goal is to have arbitrarily sized integers, and not just integers of like 7 bits or 10 bits, which is strangely something many languages seem to settle for. But I'll actually go for bounded integers. Because you can't do array bounds checking unlike a 700 sized array where your integer can be, say, 10 bits. Okay, maybe the integer is only up to 700, maybe not. And so I think having proper bounds is a far more useful way to represent your integers. So these two changes are still planned for the 0.2 version. Then, looking further, version 3, we'll want to attach clocks to our domains. I did not cover domains in this presentation because we're already at 53 minutes. I can answer questions about that as well. I have like a few slides about them. Also, array slicing. I have a master student from KU Leuven who is currently working and investigating tensor operations within the SAS language. What is feasible? What can we represent well in hardware for doing tensor operations more easily? Also, one of the bachelor students is working on a VHDL backend, and he's making mighty fast progress on that. Long-term milestones. So at some point, we'll be looking at a formal verification backend. Custom types is something that should be far earlier on the docket than that. A built-in simulator. I wouldn't say remake a simulator, but instead take an existing one like Surfer and add the potential or the possibility to shift signals back in time such that we can more intuitively work with pipeline designs. Calyx or circuit compile targets, because they have rich ecosystems of various tools that could be useful. And actually, I think also one that will be coming sooner rather than later, possibly, I would say like a year and a half out or something, would be higher order modules. And for this, I'm specifically looking at, say, DDR access. PC squared, we have these FPGAs, they have really big fat DDR banks or HBM banks. And we want to access them, but we wouldn't want to plumb the control signals all the way up and down the call stack. So we need some way of dealing with these signals. And higher order modules seems like a really convenient way to do that. This is the team. So on the left, that's me from PC Squared. In the middle, that is Patrick Beaert, our master student working on the tensor features. And on the right is our lovely bachelor's group. They are working on smaller tasks. So the VHDL backend, a website, and we're also looking for floating point wrappers for doing some real computation stuff at PC Squared, because PC Squared is really our first target audience for this language. So that is all. If you want to try it out and you have Rust installed, you can just install the SAS compiler using cargo install. If you want to try out the VS Code plugin, you can get it on the VS Code store or install it through a command with ext install Lennart van Hirtum SAS LSP. Our repository is on GitHub, and you can reach us through that QR code. This was my talk. I hope you enjoyed it, and I welcome any questions. Mm-hmm. So right now in the standard library, we have a bunch of modules to, kind of like with Rust unsafe code, to get around the type checker where needed. So we have a cross-domain module where we can cross signals from one domain to another. This is looking forward to clock domain crossings. We also have a latency offset module to offset your latency value without adding registers. Further, so with the standard library, we could provide, say, memory blocks or FIFOs in the standard library. The question, of course, is how cross-platform are they? Like maybe we have then a bunch of SAS code that compiles well on one platform but not so well on another. I'm not quite convinced yet of having them be part of the standard library or something that we have libraries of specific building blocks that you can use for using specific platforms. I think that is certainly the start, and if we find a lot of overlap between them, then we would merge them into the standard library. Other than that, yeah, various utilities. Repeat, like create an array of repetitions of a value. Things that are so basic that no compiler could miscompile them, basically. Does that answer your question? Okay. You mean dynamic scheduling? Yes. So in SUS, we only do static scheduling through the latency counting system. For dynamic scheduling, what you would have to do is you would have to declare a multi-interface module, where basically you have a input interface where you say, okay, start the module, and you need to have that extra control wire to tell it to start, of course. And then you will have I call it a trigger, where the module will then trigger the output through one of its interfaces that says, okay, the computation is done. Here is the result. The semantics of one SUS interface, let me see, like for instance here, the semantics of, say, this interface here is that in the clock cycle that, say, we have this start and this values value, they correspond to valid finish and result values 36 cycles later, always. This is the semantics of how you define such an interface. And so indeed, if you want to have a dynamic one, you need to have multiple separate interfaces. Mhm. Yes, so indeed, I want SUS development to be really snappy, exactly such that you have these small incremental updates. Certainly because any update can actually trigger any Turing complete code to go and execute to then have your developer feedback. So this is why we made the very conscious choice to use tree-sitter for our parsing front end. Because with tree-sitter, not only does it have a, how do you say that? It's a tolerant parser. So like syntax errors that you write in your file, they will correspond to like syntax error nodes in the parse tree. And it contains it contains ways to partially reparse files. So you can tell it where an edit has happened, and then it very quickly, there's a really interesting talk actually about how tree-sitter works, and it just convinced me on the validity of it. Of course, right now, this is not a humongously important item on my radar, but all of the development I do on the compiler does have this in mind. And so if we get to it, or if some very enthusiastic developer comes along and goes and implements it, then we would be very happy with that. But definitely, the compiler is built around being able to support it. Yes. Sure. It's, I mean, with like this bit serial matrix multiply, it's instant. Like you can just, maybe I can demo that real quick. Ooh, unplanned demo. That is gonna be dangerous. Where is it? Unfull screen it. Let's see, I'll move that to screen and I'll open code. And then I'll switch over to the bit serial matrix multiply. Ali. Sure, save. So you see here the editor, all of the colors have come up. And so some of the things you can do is you can hover over it and it tells you what clock domains, or well, what domains they are part of, latencies that it knows about them, etc. So you asked about compile times. So basically any edit is right now a full recompile of the project. And so if I go module test toot, so it, like you can see, the errors, they show up nearly immediately. And also, okay, I mean, for this part, it goes through the entire compile chain except generating the actual Verilog code. So I can also create a little terminal, and I can say, okay, cargo. I have actually a little script, cat make, which is just calling the syscompiler there. And I give it the standalone file, such the standalone tag, such that it puts all of the generated Verilog for this module in one file. Makes it way easier to include it in like a Xilinx Vivado project. And so I just do make, and that does a whole damn it. See, this is why we don't do demos. But yeah, the one that the LSP is using there, you can see it is quite snappy. And look, this one crashed really fast. So yeah. Yeah, so indeed, I just don't have the shift operator in right now, partly because I haven't fully settled on what the integer sizes of the outputs of this shift should be. Like, say you do like if you do a shift left, should that be equivalent to doing a multiply by 2 in terms of the range, or are you talking more about bits? Maybe if you're talking about shifts, then should you allow that on integers? Yeah, because doing a shift is more of a bitwise thing, right? Yeah, so maybe you can require that to be, yeah, to be or to have like a convert to bits, do the shift and convert back. But there is some internal discussion about having something called guaranteed optimizations, where indeed we can say, okay, if it finds a multiply by a power of 2, then we say, okay, we will output a shift from the syscompiler itself. All right, 48 here. Yes, actually I can show you this error in real life under bit serial matrix multiply dot sys. It is here. The error is unused port value, because this fixed size iterator, I'm just using it to shift 32 times, but it actually also has a port providing the integer value it's currently on. And so I didn't have a module yet to like discard an unused value, so that's why it throws the warning. And I mostly just added the unused ports warnings just so that I had some warning in the language, so I could test that warnings also work. We're still somewhat early development, but I mean, many nice things are already in, right? All right. Was my pleasure.